Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 16. We're in part 8 of chapter 3, and in this video we're going to talk about unbalanced one-way ANOVAs or one-factor experiments. So we're not going to go over an example. We're going to talk about what is different, and there is some very big differences between unbalanced and balanced. There's some major results of this. So a balanced design, of course, means that every treatment level has the same number of observations, and so we can just call that little n. So J goes from 1 to n for every level of I. In the unbalanced design, we'll change n switch it out with n sub I. Now, if you have a balanced design, then that design is robust against small departures from the assumption of equal variances. So if we have a balanced design and we are more on the borderline of whether or not we have equal variances across each of the treatment levels, then a balanced design is going to handle that okay, and we're not going to have to adjust our results or do something else. We don't have to run an alternate test or analyses. It will be fine. Also, when we have a balanced design, then the power of the test is maximized, and that's a very good thing. That's exactly what we want. We want a high power. And the power is the probability that we reject H0 given that H1 is true. So given that the alternative is true, we reject the null, which is what we're supposed to do. And when we have a balanced design, we could prove it theoretically, but I don't want to take that time in this class. We could certainly prove it theoretically that this is the case for a balanced design. We maximize the power. Okay. Now, the Ftest for an unbalanced design, the Ftest is significantly affected by even one variance among the A treatments that is different from the others. Okay. Also, the bigger the difference in sample sizes between the treatments, the worse or lower the power. Okay. Now, you'd say, well, then why do we ever use unbalanced designs? Because we are not always able to control the situation. We may attempt to do a balanced design, and then if it's a study, one of the people drop out before the end of the study. Well, now, or they don't show up for the study in the first place after they've agreed to show up for the study. So we're sometimes left with no choice, or we may figure out that we had a measurement error for one of the observations, and maybe our testing is destructive, so we've destroyed that sample, and now there's no way to measure it because we had a measurement error. Okay, so we're going to have for the means effect, or means model. This is the means model. We can call it the means model. We can use it, or we could use the effects model, which is Yij equals mu plus tau I plus epsilon ij. So we have two different models that we can choose from, and I goes from 1 to A, and J goes from 1 to Ni. So our parameter that we want to estimate is mu, and it's still y dot dot bar, but it's calculated a little differently. Now, instead of having 1 over a times little n, we had to pull the n sub I inside the summation that has I as an index. So we still have the sum of all the observations, but when we're in the ith treatment level, we're going to add up those and divide by n sub I. And then we're going to calculate the next treatment level mean, and or not mean, the sum of the treatment levels. Yeah, I guess it is a mean. And then we do that for each value of I, and then in the end we divide by 1 over A. And then for the ith treatment level, mu sub I, we have 1 over n sub I times, instead of 1 over n, it's 1 over n sub I, and J goes from 1 to n sub I of Yij. So we're summing that. And then tau sub I is calculated exactly the same way. Remember that if mu sub I equals mu plus tau I, then tau sub I is equal to mu I minus mu, and this is estimated with yi dot bar, and mu is estimated with y dot dot bar. And then we have the estimate of sigma squared, and so this is a pooled variance estimator, S sub p squared. And so now we have n sub I here. We still have n minus a, but now capital N is the sum of the n sub i's from I equals 1 to a. Okay, so we're changing the formulas a little bit. The great thing about this is when we're using a computer program, it automatically does the calculations, so we don't have to adjust these unless for some reason we're doing it manually. Okay, then the ANOVA table is exactly the same, except that we have n sub I in the summation. So here we cannot reduce SS treatments to n times the sum from, and this is supposed to be j equals 1 to ni, so that's a mistake. And so we can't reduce this. In the balanced case, it becomes n sum of yi dot bar minus y dot dot bar squared, and so I equals 1 to a. So that's the balanced case. We can't simplify it to that level because n has a subscript on it, so it has to stay in here. Okay, then the error. So again, the same formula, except we're switching out the n with the n sub I, and then everything else is the same. We end up with the F statistic is still MS treatment divided by MS error, and we have the same degrees of freedom. It's just that we calculate them a little differently. Here we cannot say a n or a n times a minus 1. We can't do that, which is a n, nope, little n minus a. We can't, this was n previously, so now we can't write it this way. We have to leave it as it is here, okay? So, or we could say the sum of ni minus a if we wanted to, but that's a little more writing, so we usually don't. All right. Now, we're going to calculate the confidence interval for the treatment means. It's exactly the same, except now, instead of having n, we have n sub I here. And so everything else stays the same. yi dot bar minus, and this is for the treatment means, which are mu sub I. So yi dot bar minus our critical value times the standard error of the mean. Yi dot bar plus the critical value times the standard error of the mean. And we can do this for any of the A different treatment means. And then we have the confidence interval for the difference in treatment means. Well, now, instead of having 2 MSE over n for the balanced design, we now have to break this up and just say 1 plus n sub I plus 1 over n sub I plus 1 over n sub k, where I and k are not equal. And I and k are between 1 and a. All right. And so we see that we have the difference in means plus the critical value with the degrees of freedom of error. So the one-way case, this is the degrees of freedom of error for the one-way ANOVA. We can use this same formula and change out the degrees of freedom here with the degrees of freedom for the error in a two-way or other model. So nested design, etc. So this still works. This general formula will work for multiple situations, but the degrees of freedom error is going to change, and how we calculate MSE will change. But once we have those quantities, we can plug them into this and calculate the confidence interval for a difference in treatment means. Now, the simultaneous confidence intervals or contrast, we want to use the Bonferroni method maybe, and so we'll say R is the number of contrast or confidence intervals that we want to calculate. We switch out alpha with alpha star, and alpha star is alpha divided by R, the number of comparisons we want to make. And then we have the same formula that we did before, except that instead of 2 over n, we have MSE times MSE. We have MSE times the sum of the reciprocal of the sample sizes again. Okay. For the contrast, again, we have this linear combination of the treatment means, in this case, and we want, before we had the sum of CI was equal to 0. What we really had was n times CI, sum of n times CI is equal to 0, and we could pull the n outside, and so we'd have n times the sum of CI equals 0. Well, the n is never 0. So the only way we could have this quantity equal to 0 is if the sum of CI's was equal to 0. Well, now we have an index on the n sub I instead of just n, and we can't pull it out. So the requirement is that C sub I times n sub I, those sums of the products have to be equal to 0. So C1 times n1 plus C2 times n2, etc., they have to add up to 0. Okay? So that's our new constraint for this, for choosing those constants of the contrast. And then we have exactly the same formula as before, again, except with one exception. Instead of having MSE over n times the sum of CI squared, we now have n sub I, so this had to come inside the summation, and that's what we have here. So we have C sub I divided by Ni, C sub I squared divided by Ni, and we sum those up and multiply by the mean square error. And we have the same here. Everything else stays the same. Okay, so this formula always works because when the sample sizes are equal, then it reduces. Okay, so I like to show this these general formulas so that you can see the difference, and now you have them written down all in one place. So I hope that helps you. Bonferroni, again, we're going to replace alpha with alpha divided by r, where r is the number of contrasts or comparisons we want to make at once. And so this means that t, so this says, so that you understand this, t sub alpha star divided by 2 is the same thing as t sub alpha divided by 2 times r in the denominator. So whichever way you want to think of it, you can do that. So we substitute this in place of these to use the Bonferroni method. Now, we also previously talked about the case of standardized contrast, where we make we divide by, remember that the sum of the CI's was equal to 0, so the mean is 0. Now, if we want to standardize them, we need to divide by their standard deviation. So what we do is we divide by the sum of CI squared over Ni, okay, and the square root of that. So we've divided by the standard deviation. So this means that we're all of the contrast will be on the same scale. Okay, so this is useful when you have different units for the different treatments. Okay, or you just want to use a standardized unit, so you'll have something that has a mean close to 0 and a standard deviation of 1, right? So our hypothesis for the confidence interval, and the hypothesis is that it contains 0, right? So that this, we can, if the confidence interval contains 0, then that means that this linear combination of the treatment means is equal to 0. That means the relationship that we're setting up is that these means are all equal, or the difference in the means are equal to 0, so they're equal, versus they're not. Okay? And again, we have two ways of writing our model. We have the means model and we have the effects model. So you can say that H naught, we have the sum of Ci mu I is equal to 0 versus H1, sum of Ci mu I is not equal to 0 in the model. And don't forget, at alpha equals your significance level. Okay. So the test statistic, I hope you've noticed the relationship between the confidence interval and the test statistic. So the confidence interval if we look at this, we have in the center, we have our contrast. And if we were to isolate, if we just look at this first term here, and we were to isolate, let's see, so we're saying that this is 0, and so we would have, so what we could do is we could rearrange this so that we had the sum of ci yi dot bar minus the sum of ci mu I in the center. And so we could do that by subtracting this from all three sides. And then we would need to reverse the sign. So we would multiply through by -1. And then when we did that, we could take this quantity and divide it, all three sides by that quantity. And what we would end up is, since this is equal to 0, we end up with this test statistic here. So let me show you what I'm talking about real quickly. So we've got the sum of ci yi dot bar minus t, I'm going to just say the critical value, CV times SE, and we've got gamma in the center, and then we've got the sum of ci yi dot bar plus CV SE. And what we do is we subtract this quantity from all three portions. So we have negative CV SE of the mean, and then we'd have gamma minus sum of ci yi dot bar, and then that would be CV times SE here. And then all we have to do is we could divide all three sides by the SE, and what we end up with is negative CV is less than, so we have this, and we'd have negative CV gamma minus, so gamma is 0 on our hypothesis, by our null hypothesis, so we'd end up with minus sum of ci yi over SE, and then we've got CV. And so all we have to do is multiply by the -1. We change our sign. CV greater than sum of ci yi dot bar over SE is greater than negative CV. And so we could rewrite this as negative CV is less than sum of ci yi dot bar over SE is less than positive CV. And so what we have in the middle is the sum of ci yi dot bar over our CV here was, if I can find it, okay, it was, back up here, it was this quantity here, the sum of the square root of MSE times the sum of, so it's the square root of MSE times the sum of CI squared over NI. So square root of MSE times the sum of CI squared over NI. And so this is our T naught. So what we're left with here, this critical value, this is a negative T and alpha over 2, and this is positive T alpha over 2 n minus A degrees of freedom. So we can use the confidence interval to find our test statistic, or we could use our test statistic to find our confidence interval. Okay, so and this tells us, so I hope that helps you understand the relationship between those two, because they are related. So now, with this, we can say that the sum of squares of the contrast, is we square everything, and and take everything except the MSE. So the MSE is the mean square error. So it's not included. That's sigma squared and MSE. Yeah, that's sigma hat squared. So if we take everything but that, we square everything, we square t, and then we take out the MSE, we end up with this expression here, which is our sum of squares of the contrast. Okay? Now the critical region is that T naught, absolute value of T naught, is greater than T sub alpha with n minus a degrees of freedom. So this is the exact same critical region we had before for these contrasts. And again, for orthogonal contrast, before we had the sum of CI DI was equal to 0. If that was the case, then the contrast of C's was orthogonal to the contrast of D's, and this is the same symbol that we use for independence because they mean the same thing in this case. All right. So now that we don't have equal sample sizes, before we had n here, and of course this became n sum of ci di. I can get rid of this down here too. Not so messy. Was equal to 0, and that is only true if the sum of ci di was equal to 0, because n could never be equal to 0. But now we have to add the n sub I back in because we don't have equal sample sizes. All right. Now, Sheffey's method, and let me get rid of the rest of my scribbling. So Sheffey's method, if you remember, this is going to be almost exactly the same, but we'll go through it again. We have M, simultaneous contrast, and we're defining the uth contrast as C sub u is equal to C1u, y1 dot bar, plus C2u, y2 dot bar, plus CAU times YA dot bar. And then this is the estimate. So this is, you could call this gamma hat of u if you wanted to. So it's an estimate of gamma. And of course, gamma are the same constants multiplied by the treatment means. Of course, we don't know those values. And then the standard error of the contrast is the same as before, except before we had MSE over n sum of CI squared and under the square root. That was our standard error of the contrast. Now we have n sub I, so we have to put that back on inside the summation because it has a index, and this is indexed across I. So it's very similar, but it is different. Okay. And then we have Sheffey's critical value. Remember, that was S sub alpha u. And that was equal to our standard error, S sub C sub u, which we have right here, times the square root of A minus 1, the degrees of freedom of the treatment, times the F statistic that goes with our Ftest for the ANOVA table. So this is the critical value that would go with the, so F naught equals MS TRT divided by MSE has the F A minus 1 N minus A degrees of freedom for the one-way case. Okay, so this is the degrees of freedom for the treatment. This is degrees of freedom for the error. So Sheffey is using that F statistic and creating a nice critical value here, S sub alpha u. And then the hypothesis test, again, we're testing that the linear combination, actually I have this incorrect, so I left out the u. So this was supposed to be the sum of CIU mu I equals 0, and that should go here, and then this again is CIU. So maybe I can put the u in here. Okay, there we go. C sub IU mu sub I. Okay? The test statistic is our C sub u. Okay? So That's our contrast, our estimate of the contrast. And what we're going to do with shift phase is compare the absolute value to the critical value that we calculated. And so this is always positive, and so we take the absolute value. If it's greater than this critical value, then, or bigger in magnitude, another way of saying that, remember that our hypothesis is that the contrast is 0. So if this is much larger than 0, absolute value of that's much larger than 0, then it's not true. It can't be true. Or it's not that it can't be true. It's probably not true. We don't think that it's likely that it's true. That's the correct way of saying it. It's less likely to be true. So we would reject the null hypothesis. And then simultaneous confidence intervals. Again, I left out this u here. So let's put that back in. So it's C sub u minus S sub alpha u is less than. So we take and we subtract our critical value. And then we add our critical value to our contrast. And that gives us a simultaneous confidence interval. So this has a little bit different form than what we've seen before. Now, we've talked about Tukey's method before, but now we're talking about it with unequal sample sizes, and that becomes the Tukey-Kramer method of unequal. So the overall significance level for unequal sample sizes is, instead of equal to alpha, it's at most alpha. So it's less than or equal to alpha, and that means that the confidence level is at least 1 minus alpha, but it could be greater than or equal to 1 minus alpha. And Tukey's gives us this statistic, which is the critical value times the standard error. And again, now instead of 1 over n, or 2, instead of MSE over 2 MSE, let's see, so instead of MSE over n, we have to have MSE divided by 2 times 1 over n1, or 1 over ni plus 1 over nj, where j is different than I. Okay? Or actually, I should have a k here, because I have the k notation down here. Okay. And then we have our confidence interval, so it's the difference in means minus t sub alpha, and the difference in means, and the difference in means plus t sub alpha. And our test statistic is the same as before, but again, we have this 2 on the bottom, and we have 1 over ni plus 1 over nk here for our sample sizes. And the critical region, again, is given exactly the same as it was before. The absolute value and the difference of the means is greater than our critical value, t sub alpha. So those are the different formulas that have to be updated for an unbalanced design. So if you have questions, please come to virtual office hours. If you need help before then, by all means email me, but send me a picture of your work and a picture of the problem, because I might not have the problem available when you send it to me, so I can help you faster if you send me a picture of both of those things. Please take care of yourself, stay safe, because we hope to see you next time.